Well, good morning and welcome to physics class. And we are finished with chapter 21, going on to chapter 23. We're just hitting some highlights. These are the highlights we would have hit normally. We're not going to get into as much depth as I would have liked to, but that's okay. What we're going to do today, pull out your review page. I sent your review page along with you. We're doing the first two sections of the review page. And basically, you're going to be taking, if you take your notes onto the review page, then you're done, okay? The review page asks you pretty much for the information I'm giving you. And so if you just copy it as I'm going through it, right under your review page, you'll be in good shape. All right, now the first slide isn't on your review page, but hang on. Light is energy, and chapter 23 deals with light specifically. Actually, chapter 24 does also, but we're going to skip that chapter. But there's a lot of evidence today that light is a form of energy, which I don't think is really that surprising to any of us. We're probably fairly used to the idea that light is energy, as opposed to some sort of matter. Although there's certainly a relationship between matter and energy, as we've learned through Einstein. The electromagnetic spectrum. Electromagnetic waves include visible light and several other types of waves, which we're going to be talking about in just a moment. And they arrange them in order and makes the electromagnetic spectrum. And if you were in my classroom, I would point you to the big chart in the back wall that we have in the classroom that shows the electromagnetic spectrum. But all of the different types of electromagnetic waves, which is broadly called light, or light energy. Visible light is a very small section of that, but the whole spectrum running from end to end, all the different types of waves are called the electromagnetic spectrum. Now this is important. This relationship is very important. Waves with shorter wavelengths have higher frequencies, and there's an equation relationship, which I don't think we're going to get into, that relate this, but wavelengths and frequency are inversely related to each other. So the shorter the wavelength, the higher the frequency, and the higher the frequency, the greater the energy. So more energy is higher frequency, but you have a shorter wavelength. Radio waves are the least energetic. Gamma waves are the most energetic. And I just want to comment here. These are waves. Sines and cosines are waves. And we're going to be, if we were to get into the math of this, which you would do in a college level physics class, not so much a high school level one, that you would be using a lot of trig, a lot of sines and cos. Well, I think mostly sines actually, but you're going to use a lot of them to describe waves. And electricity and magnetism will go in waves. Light is electromagnetic, so it also goes in waves. And so the longer the wavelength, it makes sense. It's the shorter frequency. Longer waves take longer to go by. Shorter waves go by more rapidly. Okay, so there's that. Okay, so let's talk about the different kinds of waves. Oh, they mention here radio waves are the least energetic, gamma waves are the most energetic. So radio waves are produced by accelerating electrons. These are electrons going through specifically antenna, mentions in the book. But that's what causes a radio wave. And on your review page, that's asking you for relative frequency and wavelength and cause. And here's the cause for radio waves, is accelerating electrons. This is used in TV and radio transmissions, which makes sense with radio waves, but radio waves includes AM, FM, and TV. Shortwave. I think it might be another kind of radio also involved in this. Many kinds of communications. Oh yes, microwaves also. Now microwaves are on one end of this spectrum, and I should give this relatively. You're talking here very low frequency, very long wavelengths. The longest radio wavelengths go into kilometers, thousands of kilometers, but the frequencies can be as low as 30 to 300 hertz. So it'd be 30 to 300 vibrations per second. That's very, very low. Radio waves take you all the way through the microwaves, which gets you up to 300 gigahertz. So 300 billion hertz. Right? Giga is billion, if I'm not mistaken. So the range is from like tens of hertz to billions of hertz, hundreds of billions of hertz within this one spectrum. You've got radio waves, different types of TV waves, ELF waves, which are extremely low frequency, excuse me, and then microwaves. And microwaves are used in radar, which is also part of communication, but also, of course, used in microwaves, as in microwave ovens. So, but microwaves are the most energetic of the radio waves, but they're still considered lower energy than most of the spectrum. Okay, so as far as this goes, these are relative wavelength and frequency. This is long wavelength, low frequency. All right. Infrared waves. This is produced by the thermal motion of atoms. If you remember that atoms are always moving, and movement of atoms, random movement of atoms is called thermal energy. That releases infrared waves. And since all matter is made up of atoms, all matter emits infrared waves. And there's a lot of commercial uses for this. And this is what they use for a lot of your heat imaging, because infrared waves are based on thermal energy. So warmer things have more thermal energy. The atoms are moving, vibrating more rapidly, produce more infrared waves. And so you can find warm bodies that way. And so this is the next level. These are higher frequencies between 10 to the 11th to 10 to the 14th hertz, wavelengths between a millimeter and 750 nanometers. So these are what they call below red. Infra means below red. So these are shorter wavelength and higher frequency than radio, but not as much as visible light waves. Visible light waves are caused by electrons jumping levels in atoms. If you remember from chemistry class and in physical science class, we talked about the Bohr model, and the fact the Bohr model was based on the electromagnetic spectrum, that they got light coming out of atoms. And they figured out there was only certain light waves that came out of atoms because the electrons could only jump certain levels. Well, that's what this is. Electrons jumping up and then dropping down, and they release light. This is a very, very narrow band. The wavelengths on this are 770 nanometers to 390 nanometers. So the range here is only like a factor of 2, all in the nanometer range. And if you remember, I said infrared ran from a millimeter to 750 nanometers. So that's like well over 1,000 times longer than the shortest. These are only double. So it's a very narrow range. Our eyes are only tuned to a very narrow range, deep red to deep violet. In one of the science fiction stories, the guy is blind, and so they give him a visor, and it allows him to it allows his brain to interpret electromagnetic radiation. The electromagnetic radiation goes into this little contraption, and the contraption converts it so they can send it to the nerves in his brain so he can see. But they designed it so that he could see more than just the visible light waves. He can also see other waves. God didn't design us that way, which is fine. This is a continuous spectrum, just like all of this is. So it's not like there are distinct colors. They blend one into the other, which I think you kind of knew that. Okay, then we had infrared, which is below red. Light goes from red to violet. And then when you go beyond violet, you get ultraviolet. Now, these are jumping electrons, but with more energy. So these have the same cause as visible light, because remember, you're putting down causes on your review page. Has more, the greater energy, which means it has a higher frequency, shorter wavelength, but higher frequency. And there actually are 3 levels of ultraviolet radiation, which they didn't put in their PowerPoint, the details of that. There's A, B, and C. Some of these are more dangerous than others. Ultraviolet radiation, of course, comes from the sun to the earth. That's what gives you sunburns. And too much of it can actually cause cancer as well. But it can cause sunburns. I think most of that is B, they say, causes sunburn. Black light is actually UVA, which is the least energetic of these. So ultraviolet rays are, again, higher frequency, shorter wavelengths. Okay, we're going backwards. The actual wavelengths here are between 3 and 300 nanometers, between 10 to the 15th to 10 to the 17th hertz. Numbers don't even matter here. Okay, we're talking about, we need to know these in relative order, and we need to know what causes them. That's what I really wanted you to pull out of this. X-rays are the next level. These are produced when high energy electrons strike atoms and suddenly decelerate. So you're talking about free electrons moving at very high speeds, slamming into an atom, and then getting stopped, and they release X-rays. And X-rays can actually penetrate solid matter, used in medical and industrial diagnostics. Of course, you've probably gone for X-rays. I should tell you my X-ray story. When I was in Taiwan, I was having, well, it turned out I was having appendicitis. Didn't know that for sure at the time. And so they sent me to the hospital for an X-ray, and I was having serious pain in my side. And they took me in, and they promptly X-rayed my head. And after of course, I'm in Taiwan. Okay, I'm at a Chinese hospital. The nurses didn't speak much English, and I let them do it because I didn't know what else to say. When we got back out, I told my interpreter, like, they just X-rayed my head. And so they went back in. She talked to the nurse, and they took me back in and X-rayed my side. And it turned out I had appendicitis, and I had an appendectomy, and Stevie was born the next day, and that's another story. Okay, so and X-rays, again, are even shorter wavelengths and higher frequencies. We're down now to 3 nanometers, down to 1/10 of a picometer. We didn't use pico as a prefix very much, did we? But picometer. So those are X-rays. And then the last one are gamma rays. And these are produced by high energy changes in subatomic particles. And these go from 3 picometers down and from 10 to the 19th hertz up. So these are really high energy. And if you remember when we talked about radioactive decay, gamma rays were one of the things in radioactive decay, which we're not going to get into any radioactivity this year, I don't think. We're going to miss that chapter, I'm afraid. It's just so much that at the end of the year that we try to squeeze in. Excuse me, I'm having trouble talking this morning. Okay, so anyway, these are produced by high energy changes in subatomic particles, can be stopped only by very thick or dense materials, and high doses can cause damage to living things. So, gamma rays are your highest energy, shortest wavelength, so that's your relative numbers there, and it's produced by high energy changes in subatomic particles. So, you've got, all of this is dealing with very small things that are causing this, everything from high, moving electrons to stuff happening inside the atom, actually. Okay, now the second section of your review talks about sources of light, and I want to talk about 5 of them. And on your review page, it's asking you for a description and an example of each. So let's go through these. These are sources of electromagnetic radiation, like not the root cause, but where do you actually run into them. Incandescent lighting. Incandescent sources are objects that are heated until they glow. This is your traditional light bulb, which you guys probably don't see very many of anymore. They had a wire inside that got heated very hot, and then it glowed. You also will see this on an electric stove, electric heaters, hair dryers. I think you can see it inside the hair dryer. But things that are really, really hot tend to glow. Oh, a wood burner, a wood stove, wood burning will do this as well. And the frequency and color of the light are related to the object's temperature. So incandescent sources are objects that are heated. Depending on how hot they are, you'll get a variety of temperature of light, and with frequency and color are related to each other. So basically the same thing. Will depend on how hot they are. Okay, second kind are what they call gas discharge, and this is a sealed glass tube filled with some kind of a gas, and then you run electricity through it. And the electric current flowing through that tube generates visible light. This is what a fluorescent bulb is, okay? And the type of gas determines the color of light. And in fact, this takes us back. This is what they did in the Bohr experiments when they discovered the various energy levels in the atom, was because when you took different gases and you run electricity through them, you get different colored light. Well, what your eye perceives is a single color, mixed because it's mixed. Take a prism and spread them out, and you get distinct colors there. Anyway, all of that said, that's gas discharge. And you're going to find this in, again, fluorescent bulbs are probably the most common of these. Neon lights, sodium vapor lights also are. I'm not sure they do consider fluorescent bulbs in here. Let me double check here real quick. No, they don't actually mention. Fluorescent bulbs. They mention neon lights and sodium vapor lights. Okay. Then lasers. Lasers are unique. These are light at a single frequency, um, and it's a single energetic electromagnetic wave. Normally, light is very random. Okay, it's not. It's kind of like a mob of people at a store. You know, that it's just very random. Lasers are like soldiers marching in a line, and it is a single frequency. It's all in sync with itself. Laser is actually an acronym, and I don't remember what it's an acronym for. Um, Light amplification, something something. Light amplification by stimulated emission of radiation. There we are, and they can be extremely intense, and they have a lot of practical uses. They're not real suitable for area lighting, which if you've ever seen a laser, you'll notice the light is a very narrow beam. It doesn't really light up a room. But and in fact, if there's not some sort of dust in the room, a lot of times you can't actually see the laser until it hits something. So lasers are a single frequency, very intense, because of that unity. Okay, they become very intense. LEDs, light emitting diodes, and these are something that I think even when the textbook was written were not as common as they are today. Most of the lights in my house now are LEDs. These are solid-state electronic components that emit monochromatic light when a small potential difference is established across it. Okay, that's a lot of words. What does it mean? It means it's an electronic item, and it is such that when you put a little bit of electricity across it, remember we talked about potential difference back in our electricity chapter. It doesn't have to be a large potential difference. A small potential difference across it, it emits light. It's a single wavelength. Monochromatic means one color, so it's one wavelength of light. They have a very wide variety of applications and have become practical for illumination. And like the school lights now are all LED lights. They're very low power, very efficient. So an LED bulb. Now, when I was growing up, I think where we used LEDs were in the little electronic handheld video games, and they had little LEDs. And I'm thinking the calculators also had LEDs, and they weren't nearly so bright. But today they've become much brighter, and they've really become the standard, I think, for illumination. Most of the light bulbs that you're buying today are probably LEDs. And then there's what's cold light, and this is really cool. This is generating light with minimal heat. There's very little heat. Now, most of the others involve some sort of heat or electricity. These are chemical reactions. This is what they call chemiluminescent. It's a chemical reaction that produces light. And probably one of the coolest ones are bioluminescence, which is produced by living things. And this is very efficient. And of course, if you think of bioluminescence, you're probably thinking of fireflies. And that's one of the great examples. There's also some fish that have bioluminescence. And there is some moss, I believe, that have or algae that have bioluminescence. And I believe in the deep ocean, there's a lot of stuff that does the bioluminescence. But this is cold light. It doesn't get hot, which is actually a cool thing. If I understand it, the Chinese would make lanterns out of fireflies. And some people have suggested that Noah may have done that on the Ark also. I'm not sure how actual practical that would be for a year-long trip, but you could kind of attach those fireflies after using them for light for a year. Okay, that you should have just filled in 5 slots on your review page. Now, the next section's not on your review page, okay? But I want you to pay attention to it anyway, all right? So, the speed of light, and this is just going to hit a couple of highlights. There are things that you should have heard sometime in your high school career, so we're going to go over it, but I'm not going to test you on it. Well, I'm not actually testing you on a lot of this. Like I said, we're going to do some sort of a summary, I called it, probably open book test or worksheet, something like that. Okay, so the speed of light, the currently accepted value for the speed of light is exactly 299,792,458 meters per second, which we usually round to 3 significant digits at 3.00 times 10 to the 8th meters per second. And 3 sig digs works for most situations, so that helps us, and it's easy to remember then. And this is the speed of light in a vacuum. If it's going through something like a glass or something solider, it's going to change the speed significantly. But this is the kind of the standard, the reference point is the speed of light in a vacuum. Now, there's two aspects to how light travels, but one, they're looking in this section on light waves, which is that light travels outward in concentric spherical waves. Spherical meaning spheres, three-dimensional circles, and it's going out in waves, and they're all coming from the same center, concentric, same center. And we've done this in geometry just recently. Concentric circles. Well, these are concentric spheres. However, when you get and light waves travel at equal speeds through a uniform medium. So light all travels same speed through through the same medium. All light waves travel at the same speed. Now, a plane wave is the idea that once that sphere gets far enough from the center, it starts to feel flat, kind of like the Earth feels flat if you're just looking at it, because it's such a large sphere that for a small section, it's almost flat. And so waves come out, if they're far enough from their source, they're coming out as a flat wave, a plane wave, not spherical, but just a flat two-dimensional plane. And wave fronts are a series of waves, these concentric circles, the sections of them. Your book has a better, actually has a decent diagram of it, and the PowerPoint didn't. I didn't create one. But a wavefront is like the series of waves that are coming out. This becomes relevant when we start looking at mirrors and even more so lenses, which is the next chapter, which we're going to skip, but it is important. Huygens' principle postulates how light waves propagate, and he argues that these are in wavelets, and I think they use envelope as a similar kind of word, that waves are in chunks. We're going to deal, that's where you get into a particle, but it's a particle which is a wave. And so they call them wavelets or envelopes. Not going to get into major detail here. Mathematical description, the magnitude of the electric field and the magnitude of the magnetic field both act as sine waves. And so you have these equations. E max sine omega t. Don't have to get into details, but the point is they're varying. And they are in phase, so they get maximum and minimums together. They're going high and low together. However, they are at right angles to each other. The electric field and the magnetic field are at right angles to each other. This gets really, really complex, really, really fast. The math on this at college level that I did, you barely are touching the surface of it. It's that bad. Maxwell's equations. If you remember, I had a bulletin board. I don't remember which year I had it up. And I had God said, and then I had 4 math equations on the board, and there was light. Well, those are Maxwell's equations, and they relate electricity, magnetism, and light. And the mathematical understanding of light is just, okay? It's really complex math. It's closed circuit integrals, closed surface integrals, 3-dimensional closed surface integrals, which means you do an integral in the x direction, a different integral in the y direction, a different integral in the z direction, and you add them all back together. Trust me, it's not easy. Okay, and that's one reason why I'm not including this in your review page or on your test, is because this is just giving you some ideas of what this stuff is. Some of it is going to be relevant in section B, which we'll deal with in a later video. Okay, you should have all your review page filled out. Text me the guy's name that did all of the math here made the mathematical description of light. Send me his name, so I know you got to this part of the video. And hang on to that review page, because you're going to want it when we get to our summary. You're going to need to use that as a resource to do your summary. All right, have a good day, and we'll talk to you again.